Hello, here I am starting with the question number one, second part, that is cantilever shell element. Wire element I have completed in the first part. Here I am starting the cantilever shell element. For this, we are going with the part manager, 3D deformable cell. No need to change, dismiss. We have we have to take the dimension. Actually, in the AbaQus, we have to take all the units, force or measurements, everything in the SI unit. So in cell element, we are viewing the length and width. Here the depth is not visible. So here we are giving the dimension of length and width. Length is 2 meter. Okay. Here this is the width. Width in our case is 0.15 meter. Okay. 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 Done with the part. Now going to the property. Defining the proper material. General density of steel is 7850, and the mechanical property of the steel Young's modulus provided in our case is 210 to the power 9, and Poisson's ratio is 0.3. Okay, dismiss. Now I'm going with the section manager. Create cell homogeneous, no need to change. Okay, here we have to give the thickness, cell thickness, which is 0.25 in our case. So okay, dismiss. Now we have to assign this property. This one, yeah, okay. Now I've done with the property. Now going with the assembly. Create instance. Okay, okay. Assembly part is done. Now going with the step part. We have to create. Here we are going with the general case. So dynamic explicit. Okay, okay. Dismiss. Our step part is also over. So if we want to check the reaction and the displacement at a particular point, then we have to define a point node there. So for that, I'm going to create a reaction here. This int is fixed, so the reaction will be acting here. Done. And for the one other set for the displacement, displacement continue geometry here. Since the load is acting here, so the maximum displacement we want to observe. So for that we have taken there. Done. Step done. Now we have to take the history output for the reaction and the displacement. Here set, not the whole element. We have to check the reaction at a particular point only, and we have applied in the cell element. We have to apply the force in the z direction. So for that RF3. Okay, another set for the displacement. Okay, not the whole set. Displacement, displacement. We are going with the displacement in the third direction, u3, in the case of cell element. We are creating the field output. Same thing for reaction and displacement, not the whole set. This reaction, forces and reaction. Okay, for the displacement, continue. Displacement, not the whole model. Set displacement. Okay, Here we have done with the step part. Now we are going with the load. Create concentrated load. See, we have to, since the load acting at this point is 10 Newton. For the cell element, we have to distribute that load into the number of nodes that are present here, or else we have to distribute along these two nodes only. Here I am going with the dividing the total force into two nodes, one acting at this one end and the other at other edge. So for that I am taking the concentrated force, continue this node, done, smooth step, okay, 0 0 1 1, okay, amplitude 1 in the third direction minus 5. Why in the third direction? Because here we are seeing the x and y plane. Z plane is acting downward, so the load is acting downward, so we are taking is minus 5. Okay, another load case for the another edge, continue at this edge, done, amplitude 1 minus 5. Okay, here we can see why I have taken, see, here we can see why I have taken in the Z direction. Here Z direction is acting in the vertical plane, so I have taken minus Z for the downward direction. For that only I have taken the load in the Z coordinate. Now I have to give the, now I have to give the boundary condition. For this I am going to the boundary condition, create fixed end and this one here. Since it is fixed cantilever, that is fixed part, so in castre everything is 0 at that point. Okay, the boundary condition is also provided. Now finally going with the meshing. For meshing, go to the path, here seed edges, this material is going to be meshed, done. Here we can give either by size or by number. For instance, I am giving here by size. Let's observe what we are seeing. Anyway, we have to go to the convergence study, and we have to see where the value is converging. So either we can go by size or number, no matter. 0.2 I have taken is the initially. Okay, done. Now the meshing s meshing part is over. Now I'm going with the job part. Let's assign the job is cantilever cell element. Since it is, I'm analyzing the cell element, continue, okay, submit. Okay. Yeah, our analysis part is done. Now we have to see the results. For the results, we have to see the displacement. in the U, in the third direction, we are getting the maximum displacement at 6.875 10 to the power minus 7 meter. And by manually by Timoshenko beam theory, we have got the result is 6.9 10 to the power minus 7, and here we are getting the 6.87. If we round this, then it will come around 6.9 10 to the power 9 minus 7. Almost our value is matching. Now let's see the graph. Continue. Let's see the displace reaction. Only two reaction. Yeah, save as some reaction. Okay. Similarly for the displacement, save as is displacement. Okay. Now if you want to plot the force versus displacement, since the displacement should start from here, since at 0 time the displacement is 0, so we have to take negative so that it will start from here. Here we are getting the everything's right only, but there is problem in the sign, so we want to correct it. So for that we will combine both the data, reaction comma minus of displacement. Why I am taking here the minus? Because we have to inverse that so that it will start from the origin. For that purpose only. D3 plot expression. Yeah, we are getting the same. For the smooth step, the force displacement graph is like this only. It will act since the it is gradually loaded. So this one. So here I am completing the question number 1, cantilever shell element. Wire element I have done previously in the previous video. This one is the cantilever shell element. Okay, thank you. Now I'm completing the video.